Right, we're beginning our discussion right now, and we are going to be looking at more Taylor polynomials. The remainder term, right? So we must be in 5.1.2 be in a position to use the remainder Rn 0 of f of x equals this. This is extremely important because it is giving the name of these r subscript n comma 0 f of x term. But most importantly, it is giving the general formula for the remainder. So these r subscript n comma 0 f of x equals this gives the actual general formula for the remainder term. Not all the exams do this. And therefore, this is an opportunity to take note of the remainder term formula. Right. First things first, 5.1.1 is what we need to first solve. Right, so we are given the function f of x equals x times e to the minus x. And what is the question? We're asked to derive the Taylor polynomial of degree n in sigma notation. And so, this is how we proceed. Right, to find the Taylor polynomial of degree n in that form. You note, therefore, that this one here is about 0. It's about 0. So we find the derivatives. So first we write f of x is x e to the minus x. Next, we find f primed. Right, the derivative of the x is 1. I'm leaving only x to the minus e to the minus x. Next, we actually find the derivative of, we keep x constant, and the derivative of the exponential function. The exponential function always remains the same, but you multiply by the derivative of the top. The derivative of minus x is minus 1, giving us the exponential this minus x e to the minus x. The second derivative is minus that, minus e to that, plus x e to that, minus e to that, plus x e to that. The third derivative. Right, the third derivative is going to be the same as, you find the derivative of this one, which is only 2e to the minus x. The derivative of the x is 1. By the product rule here, we use the product rule here, and then we keep x constant this time around. We find the derivative of the exponential e to the minus x, which is e to the minus x. The derivative of the minus x is minus 1. And this gives us, we add the like terms, 2e to the minus x in that, which is 3e to the minus x, minus x e to the minus x. One more derivative, the fourth derivative. Right, to find the derivative of this one, which is minus 3e to the minus x. And then the derivative of the x is 1, which is minus e to the minus x. The derivative of the exponential, derivative of the exponential is this. This is minus 4 e to the minus x e to the minus x. Okay. Right, from this we're able to get f at 0 is 0. F prime at 0 is 1. The double prime at 0 is only going to be minus 2. The third Derivative for the third derivative, this one, you can write the same notation here. The third derivative, I've put it through on top here, so I'll maintain that. Right, for consistency of the notation, so it is 3 here, and this is exactly 3 there. The fourth derivative, right, so we have the fourth derivative here. Which is -4. Right. So now we need to derive the Taylor polynomial of degree n in sigma notation. Right, so we continue as follows. Then we write out the formula. So Tn0, f of x, f of 0, f primed at 0, f double primed at 0, triple prime. This one. Okay. And then it goes on here because now you have the nth derivative of that. You have the nth derivative of that. Okay. Right, we have the nth derivative of that here. Right, so this is the nth derivative. Okay, so what we get out of this? We substitute so that t and 0 of f of x What is f of 0? Right, f of 0 is 0. Okay, there's no need to put 0 there. First derivative is 1. So we shall have 1x, just x. The second derivative is -2. So that's -2 x squared over 2 factorial. The third derivative, 3. The fourth derivative, -4. Okay. -4. Right, so this is -4 x to the fourth power of 4 factorial. And then the pattern looks very clear. It's positive, negative, positive, negative. You can even go on and say it's going to be 5x to the fifth power over 5 factorial plus dot 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 plus. And then it is exactly n x to the power n divided by n factorial. But not only that, okay, Now, because the signs alternate, so we need to take care of that. But now when it's even, then it's like this. It's negative. When it's odd, it's positive. When it's even, it's negative. Right. So here obviously must be right. Let's extend it, but I need to get the line right. So when it's odd, then it's plus. Right. And then plus, make this negative. Okay. Right. Then we have one more. Right. The last one is going to be -1 to the power something. And then it's going to be x to that, but yeah, let me write like this. So it's going to be n first. Okay, there's n, and then n is divided by n factorial, and there's x to the power n. But this one, let's see now. It's always when it's even, it's negative. When it's odd, it's positive. So it must be n plus 1. Okay. Because if I just make this, if we just make the power of the -1 only n, then it's going to be when the power is 3 odd, it's going to become negative. But if it's +1, then it actually creates wonderful alternation there. Okay, so how far are we? Derive the Taylor polynomial of degree n in sigma notation like this, like that. So, right, so it must be of the form r equals 1, r. Hey, they even missed the power, the brackets here. Okay, there must be brackets here, because this is the derivative. 0 x to the power r divided by r factorial. Okay, so it must be of this form, this derivative. See how far we are from this. How far are we from that? Right. We are well set. The general term is already there. So you can write this as t n0 f of x. It's exactly the summation. The derivative, nth derivative. It's going to be -1 to the power n plus 1. Okay, n x to the power n over n factorial. Okay, so this is what we get. And these can be simplified. So a student, okay. I need to write these differently. It's R here. R there, R there, R there, R. So we're getting R here. Then we're getting R factorial. And then we're getting R. And then we're getting R. Right, so obviously we agree that now the R factorial generally is the same as what? R factorial. It's the same as R. And then you put R -1, R -2, and so on. R -1 factorial. And this means We can write this as the summation divided by r into r minus 1 factorial. So r cancels. Okay, r minus 1. Okay, so these are equivalent. These two are possible answers. Okay, they are possible answers. Where do we start with this? If r is 1, we're checking if this is the correct sigma notation of that. So when r is 1, you put 1 here, 1 factorial 1, and then it becomes minus 1 squared, which is plus, and then it's x to the 1. So when r is 2, then it's 2 factorial, 2 here, and then it's 2 plus 1 negative, which is minus 1 cubed. When r is 2, and then it's x to the second power. Okay, so this looks correct. Okay, I can think it is the correct one. So derive the Taylor polynomial of degree n in sigma notation, and we just did. We just did. We just did.
Oh.
Yes, please.
Can you go back to the first slide?
Okay.
How do you get this? This part?
Okay, that's good. How do I get that part? Great. So to get that part, so we are actually just performing differentiation. Given the function f of x, which is x by e to the minus x, the first derivative of which can be obtained using the product rule. What does the product rule state? The product rule simply says y equals fg means the derivative of this product dy dx is f primed g by f g primed. Okay. So, right, so we first differentiate x. Okay, because it's a product, so use the product rule. The derivative of x is 1. Okay, not going to write the 1. The next, you keep x constant and find the derivative of the e. E remains the same. The exponential function always remains the same during differentiation, but you multiply by the derivative of the top with respect to x. The derivative of minus x is minus 1. Right, further expansion and distribution leads to this. Next, now we must differentiate these parts because we must get successive derivatives. So this was the first derivative, and now we need to get the second derivative. So we differentiate this one. Now we use a difference rule because it's a difference of functions. Right, so e to the minus x remains the same, but you multiply by the derivative of the minus x, which is minus 1. Right, then what is the derivative of the x? The derivative of the minus x is minus 1. Then you have e to the minus x. And then the minus x, you keep it constant, then you multiply by the derivative of e to the minus x, which is e to the minus x times the derivative of the minus x, which is 1. We have minus x e to the minus x minus e to the minus x, which is minus 2 e to the minus x. Okay, so we just performed successive different derivatives. Okay, I can always discuss that. Right, so, but now then next we just replace every x by 0. Why 0? Because it's t sub n comma 0, and now we replace x has been replaced in the function f plus f of x, but now is f, the rth derivative at 0. Okay, so x has been replaced by 0, we replace x by 0. But first, we replace x by 0 in the original function f, which is of the zeroth derivative. Okay, there's no differentiation yet at this point. and we replace x by 0, and that would be 0 by e to the minus 0. Okay, 0 by that is going to be just become 0. Here we replace x by 0, which is e to the minus 0 is 1. This one is going to be 0 by whatever. It's going to become 0. So we're just left with 1. And substitutions are performed there to actually produce this. But now we actually have been able to get the correct. Yes, please, my dear. ZP, my dear. Okay, Young, let's check. Young, let's check, my dear. All right. All right. Okay, so we have this. And then now, this is Tn comma 0. We get that one. Okay, now the next thing is we do the second part. We are still given the same function, but now we are just want to do the remainder. Right, so we need to use the remainder. This is the remainder. Where C lies between 0 and x. C lies between 0 and x. What does it mean? It means C lies between 0 and x. Like this. To show that this approaches 0, this n approaches infinity for fixed x. Okay, what do we do here? For this, we already know. A couple of things we know, like we know already the formula, but we know the nth term. The nth term, this one here, is the nth derivative. Right. So if this is the nth derivative, what is it? It means the nth derivative of the function of x. Okay, I need to just copy that one down. It is minus 1 to the power n plus 1, minus 1 to the power n plus 1. Then what? Nx, right? N x to the power n over n factorial. Okay, this was the nth term of the derivative. Okay, then you have this. Okay, so it is that because at the end, what we're getting here is we're just adding these here. We're just adding these here. Right, need to mention something here. Let me not write this now. I'll write it, I'll tell you. There is something else I want to write, but I need it. But first things first, I want us to write the series we got. Right, the series we got. What series did we get? We need to check carefully here. Need to check carefully here. Right, so we have these. We have that. I want us to, what is the rth derivative in terms of, yeah, I want to write this one, for example. Okay, like we did last time. It helps to look at this pattern. Right, to make it a different color before I take it to the other side and to reason correctly. So, the nth derivative. Okay, so if it's 4 here, then you have 4. But now you have It's alternating this. It's alternating. But now it's if it's the first derivative, so the last ones are always xe to the power x, xe to the power x. But if it's the first, then there's 1 here. If it's the second derivative, 2. So there are those patterns, 3, 3, 4, 4. So what is the nth one? In terms of, as a function of x. Okay. But you can see that the signs are not always the same. Okay, let me see here. Okay, let me see. Try to check here. Okay, this one is that. This is that. If I not make a mistake here in the signs, I think this one must be plus. Okay, let's check. I think, yeah, this must be plus. Okay, I'll just with but it must be plus. But it does not, it does not affect that answer because um, it is x times and x is 0. So it does not affect that answer. But um, obviously, when I differentiated this one, it became the e to the minus x. It became the e remains the same. You multiply by the derivative of the x, which is minus 1. Right. And then here, the derivative of the x is 1. So you just have minus e. And then you have the minus x. You multiply by the derivative of that. So that's going to be minus 1. Okay, making this a plus. So these things here have opposite signs, but so we can write the general derivative in many ways. Right. So what is the general derivative here? How else can it be? How can it be written in general? Right. So there's going to be an n because if it's 4, then it's 4. There's going to be an n. Then there's e to the power minus x. Then there's going to be um an x. Okay, there's going to be an x e to the minus x. Okay. What else do we have here? Okay. Maybe we can write like these, but also we can also factorize the things. So you can also write minus that or x minus that, and then you can write e to the minus that. And then here you can write 3 minus x e to the minus x. Okay, I'm just looking at these now. And then you can write here x minus 2 e to the minus x. Here you can write 1 minus e to the minus x. Okay, that's just another presentation that can evoke a more compact way of writing this. So you always have those numbers there, but you can write it in an expanded form anyhow. Right, so let's see if it's even, it's negative. If it's odd, it's positive. If it's even, it's negative. If it's odd first degree, it's 1 is odd and is positive. So it means therefore there's minus 1 to the n plus 1. Yeah. Okay. And then now the minus the x e to the minus x is x e to the minus x, but they're alternating the signs alternate. If it's 1, it's negative. If it's 2, it's positive. So it means that there is minus 1 to the power n. Right, so this is what we get, but yeah, it can be written like this as well. You can pull out the e to the minus x out. And this gives us n minus 1 to the n plus 1. And then it gives us plus minus 1 to the power n x. Can be written like this. Okay, there are many ways, but yeah, all these methods will surely be correct. There are definitely correct ways of writing this whole thing here. Okay. what do we have now? This is what we get. Okay, this is what I wanted to agree is the derivative, and therefore we can use it here. So I wanted to write it in the derivative of x, but I did not work it out in detail. So it is exactly that one, n, which is n into minus 1 to the power n plus 1. Okay, copy the correct thing. Plus minus 1 to the power n. Then there's an x somewhere. Right, so there's an x e to the minus x. Okay, if this is the derivative again, it means when you change the n's, like if you can try these, the come here. If you make find f2, the second derivative, f2, when n is 2, it must produce this. Does it produce this? You check. So you put 2 here, there's a 2 there. And there's minus 1. If it's 2 plus 1 is cubed, so it's minus. Right, and then you have minus 1 squared, which is plus. Then there's an x, there's e to the minus x. So yeah, so this is the correct general formula for the derivative. Why do we need it? We need it because this one here is going to need the nth derivative, but we multiply it by x to the power n plus 1. This is always the case. So this is the general formula of the derivative. This is the formula of the remainder. And therefore, you need to master it. You need to memorize it. You need to write it down in your notes. It's one of those formulas you need to know because it's going to be there in the exam. So what is it? R subscript n comma 0 f of x is fn plus 1. Okay, the examiner just left some brackets here because the derivative, you must put some brackets around the power of the f. Okay, right. So what is the meaning of this? Well, the meaning of this is that R subscript n0 f of x is going to be, right now we write the f of n plus first derivative. So you replace every n by n plus 1 here. That one is easy. Right, so you have n plus 1, and then you have, what have I done here? Right, I've written an extra n. Right, I've written an extra n. So it must be n plus 1 minus 1. Right, so you have n plus 1, then you have n plus 2 plus, and then you have minus 1 to the n plus 1 x. Okay, so continue. Continue. So what do we get out of these? Yeah, I've just replaced n by n plus 1 there. So I'm going to close. I'm going to close here because there are square parentheses there. And then you have the e to the minus x. So this is the f to the nth derivative. But now then we have this. Okay. And then now I just need to replace every x by what? By c. Yeah. So I'm just writing an x there, but let me just replace it by c once and for all. So this x must be replaced by c, and this x must be replaced by c. In other words, this one must be c, and this one must be c. Good. And then you multiply these by x to the power n plus 1. And this is exactly divided by n plus 1. And you have this. Where C lies between 0 and x. The C is between 0 and x. Right, you need to show this. Okay, so we have this. This is what we need. But now we must take the absolute value of this. Right, because it is the absolute value that, so taking the modulus of this, then we have the modulus of that. Okay, an interesting question, but it might even use the triangle inequality here because we have a sum. Now we might wish to use the triangle inequality for the sum to reach the um, individual terms. Okay, we shall see what we can do. And we have this. The absolute value normally needs to reach each of these terms to actually have a positive effect on the terms. And so we're good. We can use the triangle inequality. Right. Triangle inequality. What does the triangle inequality say? All right. Triangle inequality. So we have this. So this is less than or equal to. So the n plus 1 is okay. I can even, you can put the absolute value here, but it's positive. This. Just put round brackets around it. But the absolute value is going to make this one positive. And the n plus 1 as well. Okay, it's already positive. There's no need to, right, plus, and then here, this one, it's going to be the modulus of C. Okay, there are many ways to write the thing, but 1 factorial, and then you have e to the minus C times x to the n plus 1, like this. Okay, we have this. We have this. Okay, this is fine. Okay, it's less equal to because of the triangle inequality. We have allowed the absolute the modulus to have an effect on each of the terms in the sum. So if it affects each of the terms in the sum, then we have the triangle inequality like that. Okay. Now we are in a position to take the limit of this. So we have the modulus Rn0 of x less than or equal to n plus 1, n plus 1, and then you can put some um, absolute value bars there, factorial, then you have plus, then you have C, n plus 1, e to the minus C, modulus, um, n plus 1. like this. Okay. Okay, continue. Continue. Right, so continuing now, we take the limit of this. Okay, before you even take the limit of that, this is the modulus there, the modulus there. But C lies between 0 and x. But we agree that x is between 0 and 1. So you can always right see the relationship between the c and the x. Let's take the limit. So we have the limit as n approaches infinity. What do we could do? Okay, which is n plus 1. Which is e to the minus c n plus 1. Right. And do some manipulations here, but not. Right. So this one here is the same as n plus 1. And remove the absolute value there. And write n plus 1. Then you subtract 1 from that, it becomes n factorial because the definition of the factorial is n minus 1, n minus 2, up to 3 to 1. By definition, the factorial is defined like that. So then what we're getting here, okay, continue. We continue. Right, so this is exactly that. N plus 1, e that. So this is the limit. N approaches that. X to the n plus 1. As n approaches infinity, this one is going to be 0. But also this is going to become 0. And this thing, because x lies between 0 and 1, is a fraction, is also going to be 0. The result is 0. Effectively, what we're saying is that the limit, as n approaches infinity, of Rn0 is less or equal to 0. Okay, as a consequence, what we're getting is therefore that the limit as n approaches infinity of Rn0 f of x equals what? Equals 0. Well, I mean, it is, this is equal to 0, but also the limit, the modulus is greater or equal to 0. But again, it is less or equal to 0. So this is raising the argument that there is a number on the real line that is shown by the modulus. But this number lies between 0 and 0. What number lies between 0 and 0? It's 0 itself. So it means that this is 0. And now use the remainder theorem. where C lies to show that this approaches zero when that with a fixed x. We've shown that. For, a, for x lies between 0 and 1. Okay. Always x lies between 0 and 1. Now consider the same function here. Right, the same function f of x. The Taylor series for ln x at 1 is given by this. Use these to express this as a power series for this. Write the answer in sigma notation. Okay, we saw something like this and we packet it again. So they've given us the Taylor series for of what? For ln x at 1. Okay, that's why it's x minus 1. It's at 1. But it is on the interval 1 to 2, closed and bounded interval. Use this to express this integral from 1 to x. There's a power series. Now you need a power series. So it must go up to infinity. For x between 1 and 2, write the answer in sigma notation. Okay, what do we do here? What do we do here? What do we do here? Okay, there's nothing much to do except that you need to realize something, that these are functions of t. The t minus 1 is a function of t, and also the ln t is a function of t with respect to t dt. So if you use that to express these as a power series, so you'll have that. You'll have that the integral 1 to x ln t dt. What is ln t? What is ln t? Right, so you need to continue and write here 1 to x. Then you have t minus 1. And then now you need to put this here. Right, to put this here ln t. So if it's ln t, wherever there is x, you put t here. That will be the summation. R equals 1 minus 1, r minus 1, t minus 1, r divided by r. Okay, I've just substituted this in t. And then now we have dt. For this one here, see what you're getting out of this. You can write this one as a summation. Okay, so something like this earlier today. So we're good. Okay, so we continue. Um, we'll continue. I want to say something here. So now you need to pull out the summation. Pull out the summation. That's one way. Right. You pull out the summation. And then this is dt. The only thing you can pull out is you can pull out the r. So the r is out. The r in the denominator. And then what else is there? And then you just have the integral from 1 to x of t minus 1 to the power r plus 1 dt. Okay, this is everything here. Let me see. I think that everything is there. We just need to integrate this one. Right, to integrate this one here is the summation r equals 1 minus 1 to the power r minus 1 r t minus 1 r plus 2 divided by r plus 2 r plus 2 like this. But we're not done yet. Or we have this, but this is from 1 to x. All right. So let's see now. We have the integral 1 to x t minus 1 ln t dt. We already got something. Summation r minus 1 t minus 1. Okay, let me see. T minus 1 to the r plus what? Plus 2 1 to x. And then now you can have the r plus 2 here coming out and sitting in this position. And then wherever there is t, you put the x first, which is x minus 1 r plus 2. Then next you put 1. Putting 1 here is just going to become what? 0. So you only have this. Then you're done. So the result is this one. I hope this is the correct. I hope they did not, the formula that we copied for the log is the, does not even have the factorial. Okay, because now we just let's see the scanned images. Okay, I'll just comment on that. So 2 here, 2 there. So we have here x minus 1 to the power r plus 1 to the power r plus 1. Okay, right. I'm just doing a cross check in terms of the um, um, these formulas we have in here. Right, in terms of the formulas we have in here. Right, so this must be just the answer to it. So just note that. Okay, note that. Right, by and large it looks, yeah, it is correct. It is correct. Right, so this is 2. Right, this is 2. Okay. But yeah, that is the method anyhow. So it means therefore now for us to integrate this which is t minus 1, the ln of t dt is equal to this. Okay. And the question was, the Taylor series for that is given by this. Use this to express this as a power series for x between 1 and 2. Okay. And this is it. Right. The next thing now is about the Riemann integral. And obviously, we have seen this before, but we're just practicing to make sure that we understand this. A question that is repeated a billion times has just been the Riemann integration. State the criterion for a function f to be Riemann integrable on a closed and bounded interval. So we repeat this as such. 6.1. We start by saying here we actually let f be defined by on the closed interval AB, then f is Riemann integrable on AB if and only if and only if, right, for every epsilon positive there exists a partition P of AB such that U of P, right, such that U of P minus L of P is less than epsilon. Okay, and that is by and large how you need to state it in the exam. Right, so in 6.2, you have this quadratic. I just decided to pick this one because it is actually having quadratic. And now it's just obviously of the partition there. It's pretty much the same partition all the time between 0 and 1. Right, between 0 and 1. Calculate LPN, UPN. Hint, the sum of the squares is this. So we actually note these things here. But I want to mention in passing, normally we use a couple of these formulas. Now, the formulas we use, like the sum of the squares, are these. Okay, that's correct. The sum of squares. And then we have the sum of the cubes. This sum of the cubes. Okay, these formulas become useful when we are actually performing the integration. So it's very important to mention that. So we agree that the sum of the squares are exactly that one there. Okay, there's a typo. Whoever did this here. Okay, it must be n to n because it is exactly in terms of the uh, last term. Okay, so you just know that one. Okay, we're just starting now. And then obviously I want to state also the formula for the cubes. Right, the sum of the cubes, we did the sum of the cubes last time. Right, the sum of cubes. Right, so in the sum of cubes is exactly something we did yesterday. And so what is the sum of the cubes? Right. I just want to write that in the formula so that we can have them. And then you can also note them and remember these, okay? Because first things first, you need to make sure that you have the sum of the cubes. Because when you are faced with a problem, what you do? You just use the sum of the cubes formula to approach the question. Okay, we did that one. But now, right, right. So the sum of the cubes. Right. So this one must be n out of 6, n plus 1 to n plus 1. Okay. And then now I'm going to write the formulas here. I have lots of space. So the sum of k cubed, k equals 1 to n. Okay, it must be a function of n. So this one is exactly n into n plus 1. You can prove this, but yeah, it's not, it's not, it's school work, it's metric to prove this. Right, so we have n squared into n plus 1 squared because these are just basic series. And then now it's mostly done in school, in high school to prove this. Right, and then now we continue. And then now, okay, we have the sum of the cubes are there. And then what about the sum of the natural numbers? The sum of integers and integers, the sum of the n integers. Right, we did that one. And so we can always have that one. Okay, gonna give your right. So I'm just gonna write. I'm writing these things here. Right, the sum of the k when k is 1. We use this all the time to n. Okay, so this one is exactly n into n plus 1 over 2. Right, so we have written this. Depending on the examiners do not go high enough. They don't go because the aim is just to test the concept here. It's not to just, it's not fault hunting. So if you have k to the fourth power, k equals 1 to n, which is 1 over 30. Okay, this one has already been simplified. N to the fifth power plus 15, n to the fourth power plus 10n cubed minus n. Okay, so right, so some of the formulas that we use, okay, so just a note. Right, so we're back to the question now, and we're saying we have this. So it's very important to analyze these and have a graphical representation of the function. This is a quadratic function from grade 10, right, because now the general one is of the form ax squared plus bx plus c. Okay, I'm going to be a little bit faster to finish this off. Okay, but obviously we agree that the b term is 0 here, making it a grade 10 question. Right, now, how does this graph look like? Okay, so it will have a maximum vertex like this. Have a maximum vertex at 4. It's going to cut, have 2x intercept at minus 2, 2. Okay, just analyzing this. Okay, it's very important. Between 0 and 1, between x equal to 0 and x equal to 1, the function is here. But clearly the function is decreasing. Okay, it's very important to note that the function is decreasing, because if a function is decreasing, it means there is a point here that has x I minus 1 and fxi minus 1. All right, so we have the next one is xi and then fxi, like this. Okay, so we have this. So we have this. Okay, so those are the kinds of things you need to know. But now, if the function is decreasing, which one is the infimum, which one is the supremum here? The supremum, the infimum. Okay. Why am I even mentioning supremum and infimum? So, yes, okay, mentioning those. But now there's big M and small m, the notation we use. Okay, the big M is the supremum and the small m is the infimum. Right, so you have the capital M and then you have small m. Which one is the big M? Right, the big M is the, at this point, it's going to be the one that occurs before, which is fxi minus 1. And then the small m, like this. All right. Okay, so we have this. Right, so we have this. Okay, so let's find these. So let's find first which one. Right, so you choose the one that is easier to deal with, either LPN or UPN. But the one that is easier is one that does not have a minus one, because the minus one also is going to add a term that's extra to simplify. So it's good to do that at the end. Let's do the easy one. Right, so we're going to first do this small mi. There's fewer terms, a little bit. And the small mi is fxi, which is minus xi squared, because it's minus x squared plus 4. And then what do we get out of this? The partition, right? So the partition has this one. So these things are like I over n. This. So this one, the xi is just going to be I over n plus 4. Goodness me, we get this one. And then now we note that our delta x is 1 over n. Hence, so the small mi is for the LPN, which is a summation, right? Summation of the small mi delta x from I equals 1 to n. Okay, all right, is what we get. As a consequence, then we have this. What is this? Okay, the small mi is there for this. I squared over n squared plus 4 delta x. Okay, we know the delta x already. What is the delta x already? The delta x is 1 over n. It's 1 over n. Ah, 1 over n. Right, so it's 1 over n. Like this. Okay, so when business now we can multiply through, etc. The only variable here is I. Everything else can be taken out outside the sign. So it's minus 1 over n cubed, the summation, plus 4 over n, 1. So, so you have this one. The sum of the cubes is this one, n squared. So n squared into n plus 1 squared over 4 plus 4 over n I equals 1 to n. Okay, you're adding constants 1, so it's n by 1. Right, so n squared cancels the 1 n squared from the cube, giving us minus n plus 1 for n plus 4. Right, so we have this. Okay, so we can do many things with this. And write n squared minus 2n minus 1 plus 16n. Okay, just adding these things up. Right, so we have minus n squared plus 14n minus 1 over 4n. This can be written as minus n over 4 plus 7 over 2 minus 1 over 4n. Right, the observation therefore is that our LPN right, so the observation is that LPN is minus n over 4. Let's see now. Okay. Uh-huh. Okay, this is small typo. We can't have this n alone like this. Okay, because it's gonna approach infinity. This. So we must have this one is n cubed that arises from this is a cube, and this is squared from there, and the 1 over n is that, so that's a cube for sure. And then this one is going to cancel 1, giving us only n minus the square. So this one is going to have higher order. Okay, I'm gonna check this up. I'm gonna check this up, but yeah, my worry is this one here. Because if you simplify this, it's gonna be having an n there. Okay, I'm gonna check this. Let me do UPN. Right, you can be able to track the error. Right, so if you do UPN, use the summation up to n, I equals 1, then you do the big M. Okay, so you have the summation. Okay, the big M is gonna be what? It's this one. It's this one, which is exactly F xi minus 1. Okay, so we have this. Okay, so I minus 1 is going to be the same as one of these. Right, so it's going to be I minus 1 over n squared minus plus 4. That is the function. Okay, that is the function here. Right, that is the function. And then now the change is 1 over n. So what is this? Right, you multiply by the 1 over n. It's going to affect this one. It's going to become a cube. And the minus, so it's going to become minus 1 over n cubed. The summation cube squared plus 4 over n summation which is UPN minus 1 over n cubed. Which is I squared minus 2I plus 1. And then 4 over n. The summation of that one is going to be n by 1. Okay, the UPN and LPN must differ by normally just the minus term, negative term. So this one is going to be the summation of the I squared minus 2. Then we have the summation of the I plus the summation of the 1. Constant term plus 4 over n by 1. And then this is UPN minus 1 over n cubed. Okay, now the sum of the squares. Okay, let me see what I did. What is sum of the cubes? Oh, here's the mistake I did. Okay, because this one is it should be I squared and cubed. I need to change this. You can see that something is not balancing here. I'm going to just make a change here, please. Because this sum is going to be an unbounded sum. It's going to increase without bound. It's going to reach infinity or negative infinity because of that typo. Right. As I said, if you multiply by n, it's going to be n cubed, but the I is squared. But you can see that now I wrote a cube there. So it's going to affect the answer. So it's going to become a square here. Okay, it has been square. I'm wondering why I wrote a cube. N by n is that, so it's 4 over n, so it's okay. So now we're going to have the sum of the squares, which are these. N over 6, n into n plus 1, into 2n plus 1, divided by 6. Right, so plus 4 over n. Then here you have n by 1. So the n divides here, giving minus n plus 1 into 2n plus 1. Okay, so it is going to be 6n squared here, plus 4. Multiply this and that, which is 2n squared, 2n squared, plus n plus 2n squared, no, plus n plus 2 and 3n, plus 1, divided by 6n squared, plus 4. And therefore this, if you divide, it's going to be minus 1 over 3 from this. And then next, 3 divided by 6 is a half, minus 1 over 2n, minus 1 over 6n squared plus 4, right? So what do we get in here? Six n squared, yeah, 4 minus 1 third, 11 out of 3. Okay, this is perfect. It looks perfect, perfect. But we're gonna see the other one. So now here we have the sum of the squares. N into n plus 1 to n plus 1 out of 6. This one is n into n plus 1 out of 2, n by 1, by plus 4. Right, we get this one. Yeah. So what is all this here? You can write minus 1 over n cubed and deal with the inside here. So this one, so it's 2n squared plus 3n plus 1 out of 6 minus n squared minus n plus n plus 4 minus 1 over n cubed 2n cubed 3n squared plus n minus n squared. Minus 1 over n cubed. This is n cubed over 3 plus n squared over 2 n over 6 minus n squared. Where we have this minus 1 over n cubed n cubed over 3 n squared over 2. Let's see. N over 6 minus n squared. Okay, so we have the n squared. I hope I copied everything correctly here. Okay, minus 1 over n cubed. And then now we have n squared over 2 minus n squared. So this is n cubed minus n squared over 2 plus n over 6 minus 1 over 3 plus this cancels out, and then it becomes 1 over 2n minus 1 over 6n squared. Let's take a chance to compare these. So normally these must differ by a sign. So, there's something out here. I missed the 4 here. There was this 4, 4. So I must add the 4 here. And then if you add the 4, so this one is going to be 11 out of 3 plus 1 over 2n minus 1 over 6n squared. Okay, let's write it down, see how it differs from the other one. Okay, so the integral very likely is just going to be 11 out of 3, and the rest will approach 0. Okay, makes sense here. Right, let's look at LPN. We put it from the other side. It's 11 out of 3. If you like, you can start by writing the 11 out of 3. Right here, easy to compare. Minus 1 over 2n minus 1 over 6n squared. 6n squared. What is the square missing here in the U? Okay, I'm the one who just is a square here. This one. All right, so that's fine. Right, this look very, very correct. So we have found this here, the UPN and the LPN. Normally they just differ. One term is just going to be negative and the rest of the terms will be the same. So you can see the middle term is the one that is just negative there in the, it's negative in the lower one, in the lower Riemann sum, and it's positive in the upper Riemann sum. Okay. Right, let this speed up, calculate LPN, UPN. We've just done that. All right. Now use your answers in 6.1, 6.2 to prove from first principles that F is Riemann integrable on that. So, hey, so we have the two things, the LPN, which is equal to what? Which is this one, 11 over 3 minus 1 over 2n minus 1 over 6n squared. 1 over 2n minus 1 over 6n squared, UPN. 11 over 3 plus 1 over 2n minus 1 over 6n squared. So as a consequence, right, so you can find the limit of this LP now. Limit as n approaches infinity of the LPN. Limit as n approaches infinity of 11 out of 3 minus 1 over 2n minus 1 over 6n squared. And this is 11 out of 3 LP. Okay, so, but also we have this one here, which is the limit. But first, we can write UP. You can write UP. Right, you can write UP is the limit as n approaches infinity of UPN, which is the limit as n approaches infinity of the, which is 11 out of 3 plus 1 over 2n minus 1 over 6n squared. As n approaches infinity, which is 11 over 3. Okay. But because now, obviously, then the implication is that hence, you can see that these are equal to each other. They're both 11 out of 3. Hence, LPN is equal to U. No, wait. This is only UP. It's not UPN. Only UP, this one. So in other words, LP is UP. Right, LP is UP. Is equal to 11 over 3. LP is UP equals 11 over 3. Like that. And thus F is Riemann. Riemann integrable. Moreover, it is these things are the integral from 0 to 1 of the minus x squared plus 4 dx. Let's use the rules of integration to verify this from first year calculus. Right, the integral of the x squared is minus x cubed. 2 plus 1 is 3, and you divide by 2 plus 1, which is another 3, and then the integral of the 4 is 4x from 0 to 1. Substitute minus 1 cubed over 3 plus 4 into 1. 4 minus 1 over 3, what is it? 12 minus 1, 11 out of 3. And this 11 out of 3 is the answer we got. So it is LP, which is equal to UP. Moreover, it means that this integral is the integral from 0 to 1 of f of x dx. The integral from 0 to 1 of f of x dx is equal to the LP UP, which is equal to 11 out of 3. So the function is indeed Riemann integrable. Okay, next. Okay, it appears that we've discussed much. What time did we start? We started it at about 8:30, right? Right, we started at 8:30. So it's 10:30. We've just done 2 hours. I did not realize that, but it's okay. Um, right, this concludes our discussion for today. And I'll see you tomorrow. And my wish that is that tomorrow we meet at, you let me know which time is best for you between 1 and 2, 1 and 2 p.m. Because let me see. Okay, let me first state this. Right, my load shedding is gonna be at what time? The load shedding is gonna be at okay. I think I already got a hint of that earlier today. Uh, zone that. Right, so the load shedding is gonna be at 6. It's gonna be at 6 p.m. So if we start at 4:30, then it's not gonna be enough. We're gonna run out of 30 minutes. If we start at 3, it will be okay. Because if we start at 3, then you can finish at 5. Then it will happen at 6. So you can start at 3. You can start at 2. You can start at 1. Please advise me about
Can
which
we
time.
start at 1 o'clock?
Yeah, 1 o'clock is perfect. All right. Yeah, so we need just to play around with this, watch this video, take notes. Please always take notes of these things. It's very important that these things you write them down, because the skill that one cultivates is writing the things down. If you write the things down, it's a skill that the exam requires, being able to write the things down. So taking the notes, writing these in a book, and then making sure that one understands the solutions. And then the next step becomes to close the solutions and see if the ability to solve this without looking at the answers is there. And I must indicate that the exam is going to be pretty much of this format. But tomorrow we're bringing new things. And we need to go deeper into a bit more general questions that relate to the exam, but questions in the material, study guide, and the prescribed textbook. Okay. Yeah, okay, that's fine. Thanks. See you tomorrow at 1 p.m.
I have a few more questions.
Yes, please.
How many lessons do we have left for Math 2613? I remember we said 8 lessons.
Yeah, we said 8
How,
lessons. Yeah, I'm gonna evaluate. I'm gonna evaluate and give you feedback tomorrow at 1 p.m. But I'll have to look back. I'll have to look back and look ahead, you know.
and I think today we were supposed to do APM 3711 on Thursdays.
Yeah, that's the thing. We're supposed to do 8 p.m. 37 on Thursdays. In fact, you're right there, but now we lost track. So um we can always slow that in tomorrow. Because we have a daily activity.
Okay, that's fine. We can do it tomorrow.
Yeah, we can do it tomorrow because we're supposed to do it today on Thursdays. Otherwise, I mean, it's left behind. The truth is, we really are doing very well when it comes to this module. But now, 2613, there are a couple of the things that we need to do would be just a series. We need to do more questions on series. Why? Because, but just that the questions on series will not be very diverse. But it's very important that obviously we are very comfortable when it comes to dealing with any question on series. The ability to choose an appropriate test for convergence is very important. Because given a series, you need to know what test to use. It's not always obvious because it's not always the ratio test that works. Sometimes the ratio test fails. Like in this module, by and large, the first question always require the vanishing condition. And then the second question will normally require the limit comparison test. And the third series question will normally require the integral test. And then you have the radius of convergence question. On series, that radius of convergence question always require the ratio test. So that has been the pattern, but it's very important that we solve a bit more questions so that you can be more comfortable. But also, after having solved more questions, it's important um, to give you exercises that can be marked. And I can see for myself because I need to be sure of the level of preparation. And now sometimes this ability to solve this is done through a bit more questions. Okay, we shall discuss that please at yeah, tomorrow at 1 p.m. I'll look back and give you feedback on content coverage. We've gone through the topics, but we still have to play around with general questions. We have seen the exam structure. We have gone through the exam questions that are popular. My expectation, therefore, is much familiarity now with the content. But can any question be solved on series? Okay, series are the most important part of this course. The tests for convergence are very important, the P series and whatnot. But it will help to solve a good number of the questions. Where will the questions come from? From a prescribed textbook and the study guide. Okay, I'm going to give you more information tomorrow. Okay, thanks. Have a good evening. Okay, goodbye.